Welcome everyone. So in this video, we're going to just go over some examples, some questions, and things like that related with, say, vibrational rotation spectroscopy. Okay. So first question here, right, is I have a spectra for HBR, the lowest two absorption lines, right, for vibrational rotational spectra is at 1035 and 1085. And so the question is what is the value of the vibrational and rotational constants? Okay. Right, so this is an absorption spectra for vibrational rotation. So delta V is equal to 1, delta J is going to be equal to 1. Excuse me, so that energy difference, delta E, right? So like your R branch, this is going to be HC, I say C and then I don't put a C, I put a V, right? HC times V tilde, okay, plus 2HC B tilde times, I believe it's J plus 1. Yeah. See, can always work that out, right? It is J squared plus 1 or plus J versus J plus 1. Yep. Okay. Sorry, this is the difference. I mean, it's like HCB. This is the difference in the J values when you multiply things out. So anyway, so it's 2HCB, J plus 1, right? So, right, these are the two lowest absorption lines. So that means it has to be J equaling 0 to 1, and J equaling 1 to 2, right? And V, right, is going to go from 0 to 1, right, in both of these, okay? And so that means that that first energy difference, right, the energy of that first line, right, which is energy over light, which is related with the energy gap, right, which, because we're given the values in inverse centimeters and wave numbers here, right, that 1035 that I wrote here, right, that's HC times 1035, which is then HC V tilde plus 2HC B times 0 plus 1. Okay, so all the HCs and such cancel out, right? So it's just 1035 equals V tilde plus 2 B tilde. And then the next line you get is 1085 equals V tilde plus 4 B tilde. So you have two equations with two unknowns. When you solve those equations, I believe you get the answer C here. Okay. And so again, C, you get those constants from solving these two equations, okay? All right. All right, so next question here, right, looking at, right, question here is which of the vibrational absorption bands for some diatomic molecule will have an increase in intensity with an increase in temperature, okay? So we're kind of looking at, okay? So for one, B here and D are not allowed absorptions because V is changing by more than 1, okay? So the question is 0 to 1 transition or 1 to 2 transition going to be having an increase in intensity as an increased temperature, okay? And the answer is going to be C here, right? 1 to 2, okay? Because, right, my occupation of the vehicle's one state is going to increase as I'm increasing temperature, right? While my occupation of the vehicle's zero state will decrease with increasing temperature, right? Because I'm going to take molecules out from that ground state and put it into excited states as I go to higher and higher temperatures, okay? So C is going to have an increase in its absorption peak height with an increase in temperature. Okay, so here, right, here we're going to look at a molecule here, ethine, right, C2H2, okay, where I'm using hydrogen versus deuterium, okay, right, and I'm looking at the spacing between the rotational lines and the P and R branches, right, as 2.352 inverse centimeters and 1.696 inverse centimeters, okay? Right, I'm going to assume my bond lengths are the same across these two molecules, okay? I want to know what is the CC bond length and the CH bond length, okay? Well, we're going to get this from the fact, right, that the spacing between your rotational lines in your P or R branches, right, is just related with 2HCB, right? And again, when you set this, right, this is going to be related with this energy difference, which is related with HC times the, the inverse centimeters of your light, right? So this is just going to be 2B is related with that, right, this 2.352 or 1.696, right? And so we're going to be using this equation, right, with the fact that I'll have two different B's, right, for hydrogen and a B for deuterium, okay, right, VH, VD, okay, and we're going to solve and simplify this equation, okay, right. So to kind of set up the problem, we need to kind of understand, right, we're going to be trying to solve for B, and B, right, is proportional to 1 over moment of inertia, okay, right, and that moment of inertia is going to be related, right, with the masses and distances. So I'm going to write the center mass is this yellow dot here that I've now just filled in as red, right, that is your center of mass, right, so the distance between the center of mass and the carbon, right, is going to be given by RC, okay, and the difference between that center mass and the hydrogen is RH, right. So given kind of that definition for these geometries, right, the moment of inertia of the rotation of this linear molecule is just going to be, right, 2 times the mass of H times RH squared, 2 times the mass of carbon times R carbon squared, right? And the factor of 2's come in just because I have 2 carbon atoms and 2 hydrogen atoms, right? And so that is what IB is for hydrogen, right? IB for deuterium, right? We assume R's are the same, and all that's changing is, right, it's 2 times the mass of deuterium times RH squared, so on and so forth, right? And so it's just the mass of deuterium is changing with the mass of hydrogen, okay? Right? And so we'll be able to solve for those RHs and RCs, okay? Right, and we'll just kind of note here already while we have kind of the molecule put up, right, that the distance between the two carbons, the carbon-carbon bond distance, RCC, if you will, is just 2RC, right, and then the distance between the carbon and the hydrogen, right, RHC, right, the hydrogen-carbon distance is just RH minus RC, right? And so if we solve for RH and RC, we'll be able to get the carbon-carbon bond distance and the carbon-hydrogen bond distance. Okay. And so again, using the fact that these splittings between your peaks is related to HCB, okay, we get that 2B for 1 here is for hydrogen, 2 here is deuterium, right? 2B for hydrogen is equal to 2.352, and 2B for deuterium is equal to 1.696, 0.696. And so simplifying, right, what we'll find is the IB for hydrogen here is 2.38 times 10 to the minus 46, okay? That's just using this relationship between IB and B. And then similarly, this should be IB for deuterium, IB2, right? So then the IB for deuterium is 3.3 times 10 to the minus 46. And so now I have the equations we derived, right, relating the moments of inertia, right, for hydrogen and deuterium, right, related with the masses and the separation distances, right. So plugging in everything, I can simplify my equations, okay. What I did to get to these simplified equations down here, as I divided by, I divided everything here by 1.66 times 10 to the minus 27, okay? So I divided this onto the other side, and so that's why I get these like 2.38 times 10 to the minus 19s, right? Oh, no, sorry. What I did, sorry, I'm just looking at this here, right, is I didn't divide by 1.66 times 10 minus 27. I just divided everything by 1 times 10 minus 27. Okay? So I divided everything by 1 times 10 minus 27 to kind of simplify the exponent a little bit here, right? To get these two equations here, which again are just two equations with two unknowns. So then I can solve these two equations with these two unknowns, okay? If you subtract the two equations from each other, you're able to solve for RH, okay? And you get RH is 1.66 times 10 minus 10, okay? And then solving for RC here, you get 0.561 times 10 minus 10. Right, and so using what we talked about with relations between RH and RC to find the carbon-carbon distance, the carbon-hydrogen distance, we get these bond distances from this spectrum, okay? And so that will be it for examples here for vibrational rotational spectra.